Hi, everybody. So I guess I'm sharing the screen, right?
Yes, perfectly.
Nice. All right. So my name is Victoria, Dr. Victoria Porozova. I graduated from St. Petersburg Polytechnic University, Russia, and then I worked with Lomonosov at Moscow State University. The topic was on light scattering from Bose-Einstein condensate and also Raman sideband cooling, basically quantum hardware on cold atoms. So we were working on CNOT protocol creation theoretically, and our colleagues, experimentators at Lomonosov, they were implementing it. At some point of my career path, I got driven towards cosmology and quantum field theory, and I was wondering how actually I could switch. Should I actually drop my PhD and go to United States, try to apply and just start again? But then I finished. My advisor, he wanted me to finish. So after I defended my PhD, I found a very nice research topic. But this research topic, guys, is only developed mostly in the United States, Stanford, and the talks I saw on YouTube, they are from Yale, Princeton, and all the top universities. And in Russia, this fundamental research doesn't exist. In Brazil, people do ADS-CFT, which we're going to talk about today, but I don't know. I think they don't really do the connection between ADS-CFT and quantum computing. So today's topic would be, today's talk would be introductory. I'll try to go slowly, and I will not talk about all the details, all the technicalities, because for me, I'm also entering this field here in Brazil. I'm right now in Brazil, so I did postdoc at IMPA, then I worked with another university and one Braun. But right now, I am mostly interested in this application of quantum computing for fundamental research. So my goal is to write a paper in 25 with some extension of this topic. So for me, I'm also kind of answering with you. So I'm studying as well this topic, but what I've studied already for some years, I can share with you today. Yeah. So I guess we can probably go, right? So today's topic is quantum when quantum gravity meets quantum computing, emergent space-time as quantum error correction code. And the idea is that in physics, when you study quantum mechanics. Many students, they study either quantum mechanics or general relativity. As I observed, there's no like how to say, when you do research, you have to choose if you do research in general relativity or quantum mechanics. And maybe sometimes some people, they would go to quantum gravity, but quantum gravity is also, how we will see right now, has many divisions. So my idea was, if we try to, because when we study quantum mechanics, and I started studying 14 years ago, what you are doing, you are zooming in and then you see discretize, for example, structure of atom, right? Like discretize energy levels. What would happen if you do the same to a smooth manifold, which we call spacetime? So it is called quantum spacetime. So what is exactly quantum spacetime? That's the topic of our discussion. And we will see that somehow quantum computing could help us in this question. In classical general relativity, space-time is a smooth manifold described by Einstein's equations, not easy to solve. And when we talk about the black holes as a solutions of this system of the equations, then we would have some singularity. As physicists, we know if we face some singularity, it means that theory face some applicability threshold, and we have to create sort of new physics. And I will show you another possibilities where you could go as researchers and physics students to study this topic as well. So, okay, sorry, I'm using mouse. All right. So yes, in quantum mechanics, we say the nature is fundamentally quantum. So our idea is that we want to quantize everything, right? We also have uncertainty principle, and we have some non-local operations as well, which, remember, Einstein really didn't like non-locality of quantum mechanics. So what if we try to combine general relativity, and quantum mechanics. So ultimate theory of quantum gravity is not built yet, but there are some developments. The idea is that we want to unite these two perspectives, and several approaches were developed. For example, one is loop quantum gravity, where the space-time is made of discrete loops, and it's not smooth at a Planck scale. Another idea is that in string theory. So in string theory, you treat particles as one-dimensional objects, and the vibrations would correspond different particles. Also, the particle corresponding gravitational force would be called graviton, spin 2, but it's not detectable yet. So as we know, string theory, this is one of the predictions, but another result of string theory we will discuss today in a talk. Another concept is a quantum form. So space-time at Planck scales is just fluctuating something, but this is more conceptual than technically, mathematically presented. And this principle we will discuss today. This is a holographic principle and arising from string theory, in fact, and black hole physics. So it suggests that all information contained in the volume of space can be encoded into its boundary. There is another approach, non-commutative geometry, and this is basically the generalization of uncertainty principle, which we have in quantum mechanics, but here it would be for operators corresponding different points of space-time itself. So what you would see is that nature would not allow you to kind of know everything about it precisely, because you would have some blurry space-time points. This is what non-commutative geometry would give you if you want to understand it from physics perspective. Today we're going to talk about holographic principle. It is ADS CFG correspondence principle. I will explain it in details. And before we start that, if some of you, for example, doesn't know about ADS and CFT, then I will try to explain it here. For example, ADS is a space with a negative curvature, curved inward like a saddle. There are more types of spacetime: curved spacetime positively, and flat spacetime. It's Minkowski spacetime. We live on Earth kind of in this flat spacetime because gravitational potential of Earth is weak. So we, in fact, use Euclidean metrics and so on. And but in fact, our universe is not exactly flat. It is slightly has non-zero curvature. So we actually live in de Sitter space, how we call de Sitter space. What is cool about anti-de Sitter space, if you watch the movie Interstellar, there is one episode where you need to transfer yourself to the other edge of the universe, and what we're having there is that wormhole near Saturn. And if you read the book Science of Interstellar, in this book, Kip Thorne, he describes how this wormhole could be made of, like a sandwich: DS space, anti-de Sitter space, and DS space. In anti-de Sitter space, if you have, for example, yourself and your friend, and you have 1 kilometer distance between you two, if you go 0.1 millimeter up in Z direction, in the third dimension, right? The distance between you will shrink up to 100 meters. And if you go up another 0.1 millimeter, it would be already 10 meters, and so on. So you see that what anti-de Sitter space, it shrinks the distance. So that would allow to transfer from our solar system to another part of the universe. This is what used. So this is the feature of anti-de Sitter space-time. Now, what we're going to consider here is that for anti-de Sitter space, we also have a concept of Poincare disk, and it is a projective model called after Poincare. And the disk model was described by Riemann, and then already by Beltrami and Poincaré used it. So what this Poincaré disk means, because I'm going to use this model, so I wanted to explain what it is here. In this Poincaré model, all the points on the disk are part of this curve geometry, but in the diagram, it's projected onto a finite region. So you have something infinite here. This manifold is infinite, right? Doesn't have boundaries, but you limit it and you project all the points inside this green area to the finite unit circle. And this is how you get the points and the curvature on this circle. So you limit it. And yeah, so interior of the circle is the projected part of this green region. The boundary of the Poincaré disk is the edge of the circle, represents infinity in area space, because you cannot achieve infinity, like you cannot work with it. But when you're working with this Poincaré disk, you have to keep in mind that those are infinite points inside here. And the distances increase rapidly as you move away from the center, and it would take an infinite distance to reach the boundary. So on the boundary, we say here, CFT lives. CFT is conformal field theory. It's a branch of quantum field theory, which, yeah. So also here, red line is the geodesic. Geodesic is the shortest path, and there are types of geodesics. They would depend, like in general relativity in a space-time, the shortest path, but the type of it will depend. It's time-like or space-like geodesic. And in de Sitter space, so now we are here, they appear as arcs. So when we will see arcs, you would know that this arc is the shortest path connecting 2 points on the circle. And these arcs curve toward the boundary due to the negative curvature of de Sitter space. The first question to you as students would be, think about how you would imagine something like that, but for de Sitter space. That's the question which we were answering. We were wondering about with my colleague too, how you would create something similar for de Sitter space. Can you even do that? But if you answer this question, your research would be close to guys who work at Princeton. So yeah, that's a good one. So the Poincaré disk also helps you to visualize the causal structure of de Sitter. For example, light rays travel on this geodesic path, and because of the negative curvature, signals can reflect off the boundary and return to the center. This is a unique feature of de Sitter, where light or signals can travel to the boundary and come back within a finite amount of time. This is de Sitter slice, two-dimensional, right? Two-dimensional slice. Admit somebody was waiting. Okay. So we have now already, when you see this picture, you just learned with me that this is geodesic. This is another geodesics. And the closer you go to the boundary, you approach infinity, basically, right here. And what happens here is that you form you can form a cylinder out of the slices like this, de Sitter 2, de Sitter in two-dimensional space. So put them one on top of each other in time and direct time along the z-axis. So you would get this cylinder, and this is why we say this is de Sitter space. And the boundary of this cylinder would be conformal boundary. So the boundary where quantum field theory would live, and all the operators and observable corresponding to them. So what is conformal field theory? It is the theory which is invariant under scale transformations, which preserve angles, but not necessarily distances. And physical examples: quantum electrodynamics, condensed matter physics, critical points, certain string theory models. What we will do today in our talk, we will connect two different theories first, right now. So ADS will describe a gravitational theory in the bulk with negative curvature. So we would use a semi-classical gravitational equations. So basically, if we want some small quantum corrections, they would be like written in some order, like perturbative order, but we would use general relativity equations here. CFT on the boundary will describe a quantum theory with no gravity. So on the boundary, you have no gravity. And I don't know, I think I didn't specify this point, but here, the dimension, we call this bulk, and the boundary has a -1 dimension. So if the bulk, for example, 3-dimensional, then the boundary 2-dimensional. If the bulk n-dimensional, n+1, then the boundary is n-dimension. And I will actually give you a cool explanation what this +1 dimension means for quantum field theory. Okay. The boundary relationship, the boundary is related to the gravitational dynamics. So let's see how it works. I think that, so this principle, we call it gauge gravity duality. It's an exact correspondence between operators and physical quantities on the boundary and in the bulk. And it's called holographic duality because of this projection. It's kind of as if you had a person in a cave and then you had light and you would get a shadow on the wall. So this would be a holographical principle. And the information from the bulk could be encoded in the boundary, on the boundary. So duality here means that we have a map. When we map gravitational physical quantities, observables in the bulk to quantum field theory on the boundary and the observables there, we would have a dictionary, we would have a exact relationship. The bulk gravity theory is encoded here in the CFT living on the boundary like a hologram. The main authors of this ADS CFT correspondence, Maldesana, this is the main paper of him, written in the end of 20th century. Edward Wheaton, of course. The good part for me, so the bad part for me is that I wanted to put much more information for you, much more really from tensor perspective and quantum correction, which I didn't. So you would have to forgive me. This is the bad part. The good part of this talk that I already have my own ideas for this research, which I was kind of discussing with my colleague. And once I asked Edward Wheaton, it was also a Zoom call, and I was actually streaming on Instagram. And I asked him a question related to this talk and my ideas. We discussed a bit because I asked open questions. And Edward Wheaton, he actually afterward, he said, good question though. So I know the research I want to do is a good one. So, and the questions I ask him, so yeah. And also Leonard Susskind. Leonard Susskind, I think, is the main leading researcher at Stanford. He also has talks on YouTube on this topic. I really advise you to listen to his talks. And holography in the theory of gravity. I mean, those guys are the fathers of string theory as well. So let's now again talk about this. So now we already a little bit understand this picture. Now let's put a black hole inside of this bulk region. And black hole formation and evaporation can be described by quantum field theory. For example, via Hawking radiation, we know that the black hole can evaporate, right? Because when you have particles, antiparticles, pairs of them, which are born, and normally they will annihilate. But because of the curved space-time near the horizon of a black hole, I don't understand. Do you see my mouse here, or I need to use something? Do you see it, right? Like a error. Okay, nice.
Yes.
Yeah, so near black hole horizon, the space-time is extremely curved. So when you have a pair antiparticle and particle, one of them would go inside of a black hole before annihilation, but the other one will escape. And it will, for the conservation energy, it would have to take some energy from a black hole. So we call it Hawking radiation. And Hawking was inspired by some Russian Soviet physicists first, but they were offering for rotating black holes this principle. He actually proved that it's fair even for non-rotating black holes. So it is, and also in quantum field theory, we can with this quantum approach to black holes, we also can prove that, in fact, information, when it goes inside of a black hole and then it evaporates, you would think that it will be, there's going to be the loss of information, but in fact, no. In fact, we can have some mechanisms how to unitary gather all the information and nothing will be lost, but the problems will be with timescales. The idea is that black hole seems not to destroy information, but it's still murky, the mechanism. It's not that clear enough, but we have some ideas. And also, we do know exactly how the boundary theory will describe the experience of observers who cross into the black hole interior. So there are two amazing ideas: holographic correspondence, which we just discussed, and quantum error correction. What is holographic correspondence? Is the best handle that we have right now to understand quantum gravity non-perturbatively, and quantum error correction is the basis for our confidence that we will able to realize scalable quantum technologies in the not too distant future, right? So in fact, they can be these two amazing and seem to be distant ideas. They can be brought together, and it's actually fruitful to think that the holographic correspondence and quantum gravity could be thought as the realization of quantum error correction. So let's see how it could be possibly done. All right. So what is a quantum error correction? So suppose you have a quantum system. Suppose you have a quantum system, and this quantum system interacts with the environment, which is in this state right now. And then after we can also imagine some unitary transformation. And after that, we'll obtain, without the loss of generality, I can actually expand the unitary transformation to complete set of operators which are there, and the index A will correspond to this A state of environment which is changed. And here's the idea is that not necessarily the states of environment would be orthogonal, but if they are orthogonal, then you would have the leakage of information, because in this case, the environment would encode the information from the system, and this would lead to decoherence. If the system and environment, they will become entangled. So the data can become entangled with the environment and we call it decoherence, happens due to the presence of noise and unitary errors, which are some non-perfect implementations of unitary transformations. Our task is to reverse the damage, but we do not control the environment. But what we can do is that we can transform the entanglement of the environment with the system into the entanglement of the environment with ancilla. So some additional qubit here. And then we can discard ancilla. And we can refresh it, and we can repeat the cycle. This is called purifying the data. We call it recovery. And this process also can be thought as refrigeration, because meanwhile, this would be heated by the interaction with the environment, but this part, the system, would be cooled. So it looks like as if you got the noise entropy, and it leaks into the system, it heats it up, but we want to flush this entropy out, and this is what error correction procedure does. And if we refresh the ancilla, then it would be thermodynamically and reversible process. So we would have to spend some energy here. And when we clean out, we can keep superposed state for a long period of time. This is the idea of scalable quantum computing with quantum error correction. To make this work, errors, they must be of some restricted type. One example is weak noise, and also not for any states, but for some specifically appropriately chosen subspace of a physical Hilbert space. And the protected states has to belong to a quantum code. So we will not have any errors on this code space. So right now, holographic quantum error correcting codes. construction of a new class of quantum code. That's what we want to do. We call it holographic code. This holographic code will realize the feature of holographic correspondence. I guess you can already see that here. It reminds you of some kind of tensor network, and it's based on a uniform tiling, like you put some tiles on the bulk, and the lattice spacing here is comparable to ADS curvature, which we saw previously, right? You can even see that on the background, we're actually using this Poincare disk. So the physical variables of a quantum code, they would live on the boundary. Logical operators, which will preserve the code space, they would live in the bulk. Also, local operators deep in the bulk are mapped to highly non-local operators on the boundary. We will actually see why they are non-local. This actually interesting feature, I think I didn't mention it. So the idea is of this whole concept is that space-time, the geometry of space-time is not fundamental. In fact, the bulk, the metric of the bulk, will arise from entanglement. So if you're a quantum physicist, you won the game because entanglement seems more fundamental and it will provide the connectivity of space-time itself on the smallest levels possible. And then what will happen is that, well, this is a toy model, of course, and everything is still developing. And also we will consider now one kind of feature, but maybe problem too, that on the boundary you would have non-local operators, but in the bulk you would have local operators, and how we are crossing from non-locality to locality, it's also an interesting part. But why is it happening? So, for example, we have this cylinder. So now imagine after 20 minutes, right? You already can see that, you understand. I wish I had something like that back in the day. So now you have this anti-de Sitter cylinder, right? And let's say somewhere in the bulk, you have a bulk local operator, and it will create some disturbance. Because of causality, you would have a light cone propagating towards to the future. So it's a future light cone. So all the how to say, you can measure the effects of this disturbance if they are inside of the future cone. But at this time, I didn't put time here, but at this time, when I created the action of bar local operator, what would happen on the boundary? On the boundary, you would not have local operator acting because, as you can see, only after some time, this error is an error of time. Only after some time later, this future cone will achieve the boundary. So only here, you can actually detect something locally. You can put your observers and you can have some local, but at this point, no. So that's why we call this operator precursor. So we assign the precursor is extremely non-local operator, as if it's like, it could also be related to the fact that that the bulk has +1 dimension. In fact, I think I missed the slides, which were really, really important. I really like the slides. They were about that bulk has +1 dimension and boundary has -1 dimension, right? So like +1 and this additional dimension of the bulk, for example, radial here, radial dimension. What is it? Because boundary doesn't have it, this +1 dimension. So radius would be associated with the energy scale on the boundary. So for example, if you're close to the boundary, then you work with the ultraviolet energies on the quantum field theory, like high energies. If you go closer to the center, it would be mapped to infrared, so low energy interaction in quantum field theory. So the idea is that when you have sometimes something not solvable in quantum field theory, something which you cannot use, where you cannot use perturbation theory, then you can use the action from the bulk, from Einstein's equation, and this would help you to calculate some correlators on the boundary. So some strongly coupled systems, something with condensed matter systems, and quantum chromodynamics, which is, I think, absolutely awesome. So basically, string theory here succeeded, right? Because this all is the result of string theory, and string theory can allow you to use this mapping to calculate already now in the lab some characteristics, but it's not for our talk, right? So as we said, the precursors are more non-local. The deeper local operator is in the bulk. I guess it's probably understandable because the future light cone, I guess, will take more time to achieve the boundary. And so precursors are logical operators acting on a quantum code, and they will protect against error for the bulk. All right. Now, I guess this would be one of the kind of most complicated slides because I wanted to put much more, but I didn't have time. So here, let's say we have a slice, right? And this is a unit circle. This is Poincare disk projective model. And we choose a subregion on a circle. We call it A. And then we can connect 2 points with the shortest path, which we call geodesic. And the green area here bounded by this geodesic is called causal wedge. Causal wedge. And you have a point in this causal wedge region, and you act with some operator. The question is, can we reconstruct the operator on the boundary from this point? And the answer is yes, we can. Yes, it's not as easy, but the idea is that here we would use a past cone, right? Because everything which is on the boundary would be in the past cone of the point X. This is how we reconstruct, and I'm not giving actually technical details how to reconstruct operators on the boundary, because this I think you can find on YouTube. It's like additional lecture for this needed, I believe. So the whole idea here is that we have also there is another type, entanglement wedge. I'm not talking about it today. And the idea here is that space-time itself becomes emergent. And also I wanted to give one simple example with a black hole. For example, if we have a boundary and then we have the bulk, and interior of a black hole lies inside the bulk. So because of this, course, an exterior of a black hole, for example, in this age, so the entanglement wedge of the region outside of the event horizon in the boundary includes both exterior of black hole and part of the black hole. So entanglement entropy of this boundary contains information about the interior geometry of a black hole. So by using entanglement entropy, you can calculate some things about interior of a black hole. I think it's amazing because we kind of know, we know nothing about interior of a black hole, say, right? But I mentioned entanglement entropy. So what is entanglement entropy? This is a very important physical quantity which we use in this theory, because entanglement entropy would quantify the level of entanglement of your system. And there are other types of entropies: fundamental entropy, Renier entropy, modular entropy, and other ones you can explore. Some of them, we have properties when we know it's difficult to compute, and not always sufficient to use, for example, for Neyman entropy. And also there is another trick, it's called replica trick, which people also use in this theory. I think I'm gonna kind of skip this part. Yeah. All right. So in quantum error correction, the entangled nature of the encoded states will allow you to detect and correct the errors without collapsing the quantum state, ensuring that encoded information remains intact. The ability to correct errors non-destructively is essential for building fault-tolerant quantum computers, but for our parts is also, it will provide the needed connectivity. For this, we also need to use this famous formula. This famous formula is the triumph of this ADS-CFT correspondence, and because the entropy on of this region on the boundary SA, it's called entanglement entropy. So it would quantify how entangled are, I don't know, the region A and complement to it, and this formula says that this entropy corresponds to the area of a minimal surface in the bulk of ADS spacetime. So the area, so entropy here would correspond the area of this part. And this formula connects quantum entanglement in the CFT to geometric quantities and ADS space. I think let's talk about it here. So the idea is that in order to, so what we learned today, we learned that if we create some code, quantum code, which would be mapped, it would map the structure of space-time, that basically it, right? This is how we encode. And for that purpose, people use some types of tensor networks, and one of them is Mera. And there are actually different types of tensor networks. I mean, first of all, yeah, different types. So matrix product states, 3 tensor networks, projected entanglement pair states, and Mera is the most popular one. Those are tensor networks. And we actually put, I had I think I lost that slide because I had a slide with that, but okay. Yes, the idea is that what can we do further? So in ADS space, the radial direction represents the scale in the dual CFT, as I said, is an energy scale, basically. Moving deeper into the bulk will mean that we probe larger and larger regions on the boundary at lower energy scales. And here you can see how we can sort of map and embed this mirror in this cylinder. So the hierarchical structure of mirror can be thought as encoding this radial direction. So radial direction is the energy scales for our quantum field theory on the boundary. And also, there is another part. Yeah, I think it would be kind of the last slide. So how to connect it. I wish I could go more into details, but next time, okay? And the Mera also can be mapped to quantum convolutional neural networks. And this part maybe we already had talks, so we will have, but you can study them. So the Mera could be mapped to quantum circuits, and quantum circuits can simulate the dynamics of space-time by encoding quantum entanglement. These circuits are inspired by tensor network models, such as this. And also, my advice is to maybe read this paper, is a good one. Okay, so Russian comment. Holographic quantum error correcting codes, they're models for the bulk boundary correspondence. The main authors. My talk is based on the work of John Preskill, the guy who switched from elementary physics and became kind of leading quantum researcher, quantum computing researcher. So yeah, I guess that's it for today, guys.